Good morning or good afternoon to folks on the backcast. This is Harry Sim from Cypress Envirosystems. Thanks very much for joining us today. I think we are still having some folks join right now, but we can get started. The topic today that we're going to cover is how to help existing buildings convert their pneumatic controls, like pneumatic thermostats, to become digital, but done in a way that's cost-effective and non-invasive, non-disruptive to your occupants. The reason why we would do this would be to improve the tenant comfort, to increase energy efficiency, to reduce your maintenance effort and troubleshooting, and it could also allow you to do more advanced strategies like peak load shedding and also get lead points. So a lot of benefits, as those of you who already work with digital buildings know, there's a lot of things that you would want to, a lot of reasons why you would want to upgrade. So again, the topic is with pneumatic controls upgrade to DDC. Now, we do have a Q&A on the right-hand side of your screen. There is a panel, so if you can type in your questions there as you go, I would be able to see them, and I would try to answer those as we go along. So I already see I have a bunch of them. I think I'm going to cover these during the talk, and if I miss any of them later, please send the Q&A again. Now, before I get started, just a brief introduction for myself. I'm the CEO and founder of Cypress Envirosystems. We're based out in California in Silicon Valley, and our company focuses on helping existing buildings modernize using non-invasive technologies, technologies that can take a fraction of the time of 15 minutes to install and without disruption and with a lot less labor. The wireless pneumatic thermostat, which is the focus of the talk today, is one of our products, and it's probably one of the ones that have most widespread use. So let me jump into, what is the problem, what are these pneumatic controls? I assume if you're on this fastcast, you probably already have a good idea, but for those of you who don't, they look like these on the upper right-hand side of the slide, right? They're made by Honeywell or Johnson Controls or Siemens Powers, and they're pneumatic because when you go and turn the little knob to change the temperature, you hear the hissing sound, that's all air pressure behind it. And if you pull the thermostat off the wall, you'll find out there's no wires, there's no batteries, there's no internet connection. This is all air pressure, these little tubes that have air pressure that modulate the dampers and the valves and, the terminal units that control the heating and the cooling. This technology has been around for over 100 years. It was originally invented by Johnson Controls in the late 1800s, and it's been really in widespread use up until probably the mid-1990s. Now, what's the problem with them? They do control temperature well, very robust. It's amazing. 100-year-old technology is still in use in some of our most prestigious buildings, and it still keeps temperature, keeps people comfortable. But compared to a modern technology, what you don't have is you have no monitoring. You have limited visibility if anything goes wrong. So if, let's say, a damper gets stuck or somebody gets too hot or too cold, then what you have is people call in and they complain, and then there's a problem and you have to go fix it. Compared that, to a modern digital system, you really have alarming, you have trending, you know of problems that you detect before people become uncomfortable. So that's a major shortcoming of pneumatic controls because you don't get that visibility. Also, what you don't get with the pneumatic controls is the remote ability to change set points, or you cannot say, well, someone is uncomfortable, or you have somebody not using a space. The office is empty, and you can remotely just dial in and change the thermostat to avoid heating or cooling. Well, you can't do that with pneumatic thermostats. You have to walk up to the thermostat, physically turn that knob to change it. And then, when you want to change it back, you physically go up there and change it again. So obviously, very labor-intensive, very disruptive. You need to go into occupant space, so that's really not done. So that's another big shortcoming. Third one is there's no backnet connection. You know, many of you assume who run buildings or have invested in your buildings, you have modern automation systems that, you know, from Johnson or Honeywell or you know, Siemens who control your building. But these thermostats, because they're not networked, they're not communicating, they're not programmable, they cannot be talking to your building automation system. And, you know, usually you talk through BACnet, which is why I wrote this here. You have BACnet or LAN, but different protocols that you can talk with your building automation system, but, you know, the pneumatic thermostats don't. I already see there's a question coming in, you know, whether the retrofit solution will talk with BMS, and definitely it does. So I'll show you, you know, in a little bit, you know, how you would retrofit these older stats and be able to go to, you know, build an integrated DDC system with your building automation system. Last thing is that is a shortcoming of pneumatics is that you cannot implement a lot of energy saving strategies, and I'll talk about that in a little bit more detail, but it's as simple as, you know, cannot do set point enforcement, cannot do deadband set points, cannot do duct static pressure control, cannot do supply air temperature resets. So a lot of modern buildings would implement a lot of advanced saving strategies, but again, because of the limited nature of the pneumatic controls, you can't do them. So, you know, that kind of explains the major shortcomings. Now, let me dig in a little bit more detail to talk about, you know, about the visibility. If you have a pneumatic system controlling your zones, you know, your thermostats, you have pneumatic actuators, then what is one of the problems is that you can't see a lot of things, and not only just the thermostat. You know, your dampers may be stuck, or you may have air leaks, or you may have oil in the pneumatic lanes or water that's contaminating it. You may have reset velocity controllers not calibrated. You know, so even though you think you're setting it to a certain temperature, it's controlling to another temperature. So all of these things are mechanical devices. They do not tell you if they have a problem. And so it's not only the thermostat, it's all these things that are around the thermostat that can go wrong that you really have very little visibility to in a pneumatic controlled building. So that's the downside of not being able to see all the details and isolate and detect the faults. Now, in terms of energy savings, the digital buildings typically use about 20 to 30% less energy than pneumatic buildings because they're able to implement a number of different saving strategies. Like it could be, again, as simple as to say set point enforcement, no higher than 74, no lower than 68. It could make sure that you have occupancy schedules, so if the office is not occupied, you shut it off at, the zone, no heating or cooling. You can do auto demand response to cut peak load. So there's a number of strategies that digital buildings normally do. For those of you who are chief engineers or, building managers, these are probably all second nature. There's nothing special about all the strategies on this page. They're used by digital buildings for the last 30 years. The only problem is in pneumatic buildings, you can't do them because you have no remote control and programmability, and then you have very limited sensor data. So, you're basically blind and you can't do any actuation in your zones, which is why the pneumatic buildings, they can't do this. And this shortcoming really is a 20% penalty on energy use, if you will. So just how many pneumatic buildings are there? And those of you who work in one or manage one already know there's a lot of them. It's probably around 70% based on data we have from the DOE and from government, U.S. federal government sources. About 70% of non-residential buildings have pneumatic controls. And what we mean is 30% is fully digital. You have digital stats, you have networks, you have your air handlers, your chillers, your boilers, all digital. But there's a good number of them that are completely pneumatic, so they don't have any digital systems at all. That's a shrinking number. That's 25% of it. And the largest segment is people who are sort of in the middle. They were able to upgrade their chillers and air handlers, but it was very difficult and expensive to get to the zones, to get actually into the occupant space, to then disrupt them, to replace the thermostat. that was too costly and it was too disruptive. So you kind of have a half digital building, and all your thermostats are still pneumatic and mechanical. So that's what we see is still the largest segment of buildings, non-residential buildings in the country. Now, you may ask, well, why don't people upgrade to DDC, right? We've had DDC for now 25, 30 years, and you wouldn't think of building a new building without DDC, and why don't people upgrade the old building? The problem is that these old pneumatic systems are really embedded inside a building, and to upgrade them, you're talking about opening up walls and ceilings and replacing actuators with, pneumatic actuators with motors. You're running wires. If you have any type of asbestos and you need to do abatement, in any case, once you open up walls and ceilings, you're talking about disrupting the tenant and a lot of labor costs. It might seem strange, but just replacing a thermostat means that there's all this labor and things behind the scenes that you have to do that it's typically average nationwide about $2,500. Be more for New York City, maybe less for some other locations, depending on whether you have expensive labor, whether there's prevailing wage labor. But typically between the materials and labor, you're talking well over $2,000. And that doesn't include any cost of occupant impact, so disruption to occupants. So because of the expensive nature, the payback period is usually over 10 years. So it's really not economical, which probably is why, many of you have buildings and you were stuck and you really cannot upgrade. Now, I'm sure I apologize for taking the time to explain the problem, but really now I want to explain how we would address it, right? So we have a three-step process for how to get a pneumatic building to become a digital building that's smart and saves energy and cuts down on the maintenance costs and so on. So I'll go through each of these steps in more detail. The first one is that we need to replace the old thermostats with something smart and digital and communicating, right? And that's the core of the technical solution that we replace those thermostats. Second is that once we have those thermostats in place, they are intelligent, they collect a lot of data, we can run analytics on them to detect faults that are sitting in the system. Now, some of these faults, like a stuck actuator or a leak, may have been there for years and years and nobody knew about it because there's no data. Well, once you upgrade to these digital thermostats, you get a lot of data. The software, which is smart, it goes through and looks at all the different data points. It would start identifying faults that need to be fixed in the system. So by doing that, you can then sort of retro-commission your building back to a working order, an optimal function. And then after that, you can implement, in a step 3, you can implement a whole bunch of energy-saving strategies that we already talked about, right, from duct static pressure control to, deadband set points and so on, and I'll explain how that works too. So it's really, the first thing, step 1 is how to do this at the lowest disruption and cost. Step 2 is how to fix things so you get immediate bump in savings and comfort. And step 3 is how do you optimize even further to get additional savings, by tying into your building automation system and implementing, that more advanced strategies. So let me talk about the first step, which is how do you upgrade your existing pneumatic thermostats. So your existing thermostat, you pull that one off the wall, and basically this system, you don't have to open up the walls and ceilings. You just take the old one off the wall, you connect the tubes back and mount it on the wall. I think I have a picture of this one here. Here, just a second here. Yeah. So you take it off the wall, you see the 1 or 2 tubes. There's a mounting bracket that fits all the holes from Johnson or Honeywell or Siemens. You don't even have to drill a new hole. Just mount it back on the wall, connect the tubes, and press the button to activate the wireless, and you have digital pneumatics, essentially. So for those of you who've done DDC upgrade before, this is a much, much simpler process, right? Traditionally, you really have to open up walls and ceilings and run wires and remove actuators and replace them, with direct coupled actuators and things like that. So it's a lot of effort to change them over. Now, once you upgrade this device from the pneumatic to this wireless pneumatic thermostat, it does a whole bunch of things. You have remote control, you have remote sensing of temperature and pressure, You have BACnet connection to your building automation system, so you can see it, on your Andover or Schneider, or Siemens systems. You can do programming for schedules and also self-calibration. So, pneumatics, you may know, require manual calibration to keep them working well. Well, these units are self-calibrating, so once you install them once, you do it one time, and it's all self-calibrating. Now, these units, they don't need any wires because they're battery operated. The wires is what costs a lot of money, right, to pay the electrician to come in and power everything. So these are battery operated. They use 2 CR123 lithium batteries. The battery life on the specification is 3 to 5 years, but actually in our lab we have them working to 8 years, and a lot of customers are really pushing more than definitely towards the 5-year time for the battery life. So it's very simple to install and very quick. In fact, for your tenants, it could be during coffee break, they come back and there's a new thermostat on the wall and it's now digital. Technology's been around since 2009. That's the first, so it's been a while. In fact, in 2012, the wireless pneumatic thermostat won the Building Operating Management Top Products Award, and we had the ACHR award in 2010 as well. So since that time, we've had probably close to about 100 million square feet all around the country that uses this technology. Now, each of the thermostats that I discussed, they replace the existing thermostat on the wall where the old one used to be. Well, we also put in a wireless mesh network. Somehow the thermostats have to communicate with what we call our green box controller, the thing that you see in the middle of this slide. That's our hub, and the green box controller acts as the scheduling control, the BACnet gateway. It has a website, so you can change set points, you can look at history. The thermostats work through this mesh network, and it's all wireless. So again, avoiding the wiring, avoiding the disruption. Comes back to this green box controller, and then we have 2 ways that you can interact with the system. If you have a building automation system like a Johnson Metasys or an Andover Continuum or Train, Tracer Summit, those ones you can integrate with all the stats using BACnet. You do an auto discovery, and all of the thermostats will pop up as new BACnet devices that were just discovered. You can drag and drop them and map them to your database, and you can build graphics around them just like any digital stat. So really, for your building automation system, it looks like a digital stat. It's a BACnet device, and it's quite easy to deal with. Pretty much, it's like if you bought a Johnson stat for a Johnson Metasys system, it would just connect right in. So that's what these are designed to look like, and a good, probably about 2/3 of our customers would use the BACnet interface to communicate and control the WPT, the wireless pneumatic thermostat. Now, in parallel to that BACnet interface, we do have our own web-based data interface, and that one is included in the green box controller. So some people like to use this one, and they use it in parallel with their BMS interface. Others just use the free one, the web-based one that comes with it. It's really your choice. There's no licensing cost, no royalty cost to that one, the free one. This one, you can change set points, you can trend historical data, you can download things to Excel for analysis, for example. So you really have quite an open choice to access the data and to do the control. Right. And I see from the Q&A here that, there's a number of people, well, can we talk with Tritium? Can we talk with Johnson? The answer is yes. The list up on the right-hand side here is not exhaustive. Basically, we are BACnet over IP compliant. So, if the automation system you have now talks BACnet over IP, then it could do exactly what I discussed. A JACE could then do an auto discovery, finds all the points, map them into the JACE database, and you can build graphics around them just like any digital stat. Right. So they are designed really to look like digital stats from digital manufacturers. And the fact that these are pneumatic and they're wireless, it doesn't make any difference how you would integrate to your building automation system. right? Now, as I mentioned, this technology has been around since 2009. One of the most critical things we've gone through over the last few years actually have the Department of Energy do a very exhaustive test of this technology, because there's so many of these buildings, pneumatic buildings around that they really have to say, well, how can we deploy these to only some buildings or all buildings? Well, basically, the Oak Ridge National Labs, the DOE labs, they did a 2-year study on a federal building in Washington, D.C., this Ronald Reagan building. And after that, they published the results, and their conclusion was, well, this is a no-brainer. Just do it in every facility that has conventional pneumatic controls. You'll be able to find a full report in this Green Proving Ground program. I should have put a link. I'll send out the link afterwards. There's a short version, like 4 pages, and then there's a full 300-page report. But essentially, the bottom line is that it works really well for pneumatic buildings, and it's recommended for use for federal government buildings, the GSA buildings. I see that there's a couple of questions about the wireless architecture here. Let me answer that as we go. So go back to this slide here with the wireless network. Basically, if you look at the green box controller, one green box controller typically can handle up to 225 thermostats. So if you have more than that, it's a big high-rise building, you have 1,000 thermostats, you just put more green box controllers, typically one for every 3 to 4 floors. Now, the thermostats talk wirelessly with the green box controller, and if the distance is too far, we have a repeater. So normally, one repeater would serve up to like 10 thermostats, and we would have up to 225 thermostats per green box, and then we have up to 10 to 15 thermostats per repeater. And I can definitely go into more detail there, but that's roughly what, and the range, each wireless hop usually is around 100 to 150 feet, and you could put a repeater, and it goes another 100 to 150 feet, and you can put up to 5 repeaters. Again, if you were in a single-story building and you have 5 repeaters, spanning out, you could go, probably 600 feet, 700 feet each direction. If you have a high-rise building, usually we put one green box controller every 3 to 4 floors, and the repeaters can bridge through the floors. So it's, again, avoid the wiring, avoid a lot of the heavy expense with labor, just using the wireless to transmit across floors to the green box controller. All right, so I talked about step 1, just physically how to get this system in. Typically, the cost of this is about $1 a square foot. And it goes from about 90 cents a square foot to probably $1.50 a square foot. Most of the time, you have one thermostat for every 800 to 1,000 square feet. So that kind of gives you an idea how much this retrofit, the upfront cost of the retrofit for just getting these thermostats in. Now, once you have the thermostats in, then, as I mentioned, we have the smart analytics that now help you to diagnose the problems. Now, in fact, the smart analytics are pretty new for us. We just started doing this end of last year. When we first started, we had a lot of data, and we graphed, all the pressures, all the temperatures, the occupancy modes, and we figured if people had that data, they'd be able to improve their troubleshooting, they'd be able to nail down all the problems with their building. But then what we found out was pneumatics is really a dying art. There's a lot of people who really don't understand how these pressure systems work, and even if we provide all the data, it's really hard for people to spend the time to pour through the data to kind of diagnose what's the problem. So based on a lot of requests from customers, we developed a software tool that would mine the data. So we collect data on like zone temperature, set points, occupancy modes, air pressure, as you can see in this slide here, and then we crunch it through our analytics engine, and it comes out in 2 types of reports. One is a more prescriptive report, like, recalibrate this thermostat, go check this damper to see if it's stuck, or go check for an air leak here. So for people who really have no time to dig deep, then, we just have a prescriptive list, go check this thermostat, go to this room, check this node, and that's the prescriptive list. Now, for those who would want to drill deeper, then we have a more in-depth report that gives you a lot more insight. So this is an excerpt. Normally you would have like each row is a room, with the thermostat, and it could be like hundreds of rows in this table. But basically, we sort this table. In the very top will be the zones which have the most problems, like, cannot maintain set point. For example, this one here with 4.7, the upper left-hand red one, means that it's not controlling temperature pretty well. That zone is on average like 5 degrees off from where the set point is. So, that's a problem. And then the yellow ones are off a little bit less, between 2.5 to 4 degrees. The green ones are pretty comfortable. They're pretty close to set point. So that first, that column with the colors, that kind of tells you which are the worst zones all the way to the medium zones, then the better ones. And as you look to the right, you can see what the likely problems are. Is it a calibration problem? Is it a main air pressure problem? Is there oil in the line? Is there oscillation? Is the actuator stuck open? Or is there insufficient heating or cooling? So there's a whole bunch of things that are very typical of, pneumatic or even just general terminal units. But what is the problem? And by looking at all the data that's, rich data coming from the thermostat, you can really have a good idea of, which ones are the worst zones and what is the likely reason for that problem, and you can go fix it, right? So that helps a lot. And for those who really want to drill in, you could double-click on any of these cells, and it would tell you exactly when that event happened. You can trace it down to what pressures and what time that occurred, whether it was occupied time or not. But, for most people, they would just look at that top list and just follow the recommendations. They don't really care to look in all the details. They just follow the list and fix the problems, and they're done with it. They have a very busy day. So basically, the analytics package really helps you with, understanding the problems. And again, they really help you to save energy, make people more comfortable, and help you reduce your labor cost. Okay, I think I'm almost running out of time, so I'm just going to skip over some of these other ones here. Just as an example, the things that you might detect, one example we had in New York City schools, they have 1,000 schools that are pneumatic, and many of the hot water valves are stuck. After many years, they're like, been there for 30, 40 years, the hot water valve is stuck open. It's on maximum heating, and then the people open the windows to get cool. Well, they never knew about this, and it's overheating for years and years. It's wasting energy, but there's no detection of this stuck hot water valve. After we put in the thermostat, they could see the problem. They fixed it, immediately just by fixing it. You got a 10% savings on the valve that they located. So that's sort of one example of how, the data can really help you to improve these energy savings. And then also, what we have is a lot of reduced hot and cold calls, so people are more comfortable. This is an actual building in San Francisco. This one, Cushman and Wakefield case study, where after the installation of the thermostat, they were able to reduce the hot and cold calls by 2/3. So, huge bump in tenant satisfaction. And we also have LEED credits. As you know, LEED version 4, you're really concerned about building commissioning, continuing building commissioning. So having this type of analytics with all the data helps you check a lot of points. If you were going for LEED points, then this whole ability to do the diagnostics really helps. Okay, unfortunately, I think I'm going too slow through this, so I'm going to go to the last part here, which is the energy savings, right? So the first step gets you the hardware and the software. Second step fixes your problems. Now, the third step is how do you get your savings? And I'm going to skip to, the savings that you would deploy. As I mentioned, this is all just like digital buildings. You would do these ones for any digital building, and now you can apply these savings to pneumatic buildings, right? So it's just at a much lower cost. You wouldn't have to spend as much money to make your building, to enable your building to do these strategies. So once you put in the strategies, typically we would save about 20 to 30% is very typical. Minimum of 15% is what we see. So each of these strategies, we save a certain amount, and we calculate this one how much you save, like 26%. Now, there's a case study that we did. This is in Chicago, a high-rise building. It's installed in end of 2014, early 2015, a 65-story building. basically it was really fast to install this. It was only took like just a little over a month actually to upgrade the building. Then the cost, again, for this one was about $1 a square foot to do. They ended up saving 30% of their HVAC energy consumption, and they were able to get their ComEd rebate, the utility rebate, and the payback period is like 1.4 years. So it's really, actually ComEd has a case study that they show, so how much did it cost and how much they project on savings. That was 2 years ago when this first got, we applied for the rebates, and now we have 2 years of actual data, and the performance was better. This building is owned by Zeller Realty, and they have a great operational team that tracks the savings. And in fact, over the last 18 months, the savings was closer to 30%. We projected 26%. They actually got about 30%. So their payback period was even better than what was originally projected, a payback period of 1.4 years. Okay, so that one was the case study for 311 South Wacker in Chicago, but we've done a lot of buildings. I have examples of high-rises here. We've done hospitals or schools, hotels. Basically, pneumatics technology exists in a lot of places, and it's throughout the country. So you can see for the high-rise buildings, from Phoenix to Chicago, San Francisco. There's a lot in Canada, in Toronto. So we see that the technology has worked really well in basically many types of buildings and in many locations around the country. All right, I want to make sure I respect the time, so I just want to summarize here, right? So here we have a new technology that can really have a much lower cost and lower disruption to upgrade your existing pneumatics. You get quick payback, usually 3 years or less, and you can get utility rebates. So maybe for perhaps for the first time, you can really have an economic case for upgrading your pneumatic system with a really attractive financial justification. All right, it is like 33 past the hour, so I'm 3 minutes over time. Yeah, let me just share with you my contact information here. You can go to our website. Again, we have a lot more other technologies that help with existing facilities, but today we focused on the wireless pneumatic thermostat. So I think we might have some time for Q&A. So let me go through the list again to see, if what we have as questions here. Okay, I think a lot of questions about cost, right? So as I mentioned, there are two ways to think about cost for this one. One is maybe an average cost per thermostat. So as I mentioned, if you use a conventional DDC retrofit, probably $2,500 or more per thermostat. This one is somewhere between $750 and $900, depending on the type of thermostat and if you have, union prevailing labor rates or not. But again, about $750 on the low side to $900, maybe $950 on the high side for the retrofit of the thermostat. Usually that equates to somewhere between 80 cents to $1.50 per square foot. It depends a lot on how dense how many thermostats you have in the building. Okay. I also have a couple of questions. Do we do summer, winter? Do we do direct acting, reverse acting, single pipe, two pipes? Sounds like there's some folks with actual buildings with all these different flavors of thermostat. So the answer is we can retrofit any existing thermostat. There are many different flavors. There's some that switch summer to winter, some with single pipe, and some with two pipes. Once we know the existing model, we cross-reference to the correct WPT model that can then directly replace that one. So pretty much all of them, you have that, you can replace the existing stat. Let's see, a couple more questions. Oh yeah, so the repeaters, how are they powered? So there's a number of questions on the network. Let me show the picture of the network here. There's a question about how these things are powered. So I mentioned the WPTs, the thermostats, are powered by batteries. So that saves a lot of wiring. They last 3 to 5 years. The repeaters They are line powered. There's two choices. They can be powered by 24 volt. They can be powered by 110 volt line power. Again, one repeater for every 10 to 15 thermostats. Usually repeaters, they don't have to be line of sight. They can be mounted above a drop ceiling. They can be mounted on the wall. And then the green box controllers, usually they are in a utility or communications data closet or electrical closet. They just plug into a 110 volt outlet, and they usually plug into an Ethernet. Have a Cat5, Cat6 cable, and you plug into the automation or the building LAN. Okay, I think there's some questions also about the type of wireless that we have. The wireless is it doesn't interfere with existing Wi-Fi. It's based on wireless keyboards and mice. So you can think your Logitech and Microsoft keyboards, your wireless keyboards and mice. That's the radio that's in these thermostats. So you can imagine, these type of radios are everywhere. There's 110 million of these around in use in the country, and they wake up. They transmit a very short burst and they go to sleep. They don't interfere with anybody. So, we're installed in hospitals. We're installed at NASA. We've gone through, the NIST certification and testing. So it's really not been a problem with interfering in the wireless. Okay, let's see if we have any more time. Let's see here. I think there's questions of whether we have this package available. The video for this webcast will be available on our website, so we'll send up a follow-up email so you can watch it again if you want to. We will have the slides in PDF available for download as well. There'll be an email coming out of Building Operating Management. Okay, I see a lot more technical details, questions, so I'll probably, you can email me based on my, my email address. I would be happy to answer them. Let's see here if there's anything else. Are there any installations in the southeast part of the country? Answer is yes. Georgia, Atlanta, we have South Carolina, North Carolina, Texas. So really it's in every part of the country. But for good or bad is we see pneumatics almost everywhere, and wherever there are pneumatics, really this is a pretty good application for them. So whether it's a hot climate or cold climate, it's been shown to have pretty good energy savings. All right, I think we're just about out of time here. So please email me. Again, show you. Let me show you my contact information. Feel free to email me, and then if you need any further information, or if you have a specific building and you need help with a more specific quote or estimate for cost, we'll be happy to do that too. And by the way, we work with a number of different contractors. So, if you have your favorite contractor, you trust them with your automation work, we can supply them with training and with materials. It could be that they already work with our products, so, you can do that. In some cases, we can serve customers directly, so, we're very flexible in how we do that. Actually, some customers, they self-perform as well, so they get trained themselves. We've had large hospitals and universities where they buy the product and then they get trained and they install it. Since it's very simple, 10, 15 minutes to install a stat, they can do a lot of the work themselves to save money. Okay, I think we are about 10 minutes after, or just 40 minutes after the hour, so I will wrap up now. And I really thank everyone again for your time. And if you have any thoughts or questions or any suggestions, we're based in Silicon Valley. We love thoughts and comments. We love to hear about problems. If we haven't solved them yet, we can work on it, and maybe we'll have new products to solve your problem. So really, really appreciate to hear from you. All right, thank you, everyone, and have a great afternoon.